My name is Mike DeLaCluse. I'm president of Lesman Instrument Company. I'd like to thank everyone for taking time out of their busy schedules to join us today for Introduction to Control Valves for Low Flow Applications. Today's presenter is Tim Gaynor, Regional Sales Manager, and Harry Wepkenberg, Product Manager for Richards Industries, which owns Low Flow Control Valves. Their other brands include Jordan Valves, Marwin Valves, Hex Valves, SteriFlow, and Vestabel Steam Traps. Tim has 19 years of experience in the industry, 16 of those years with Richards Industries companies. Harry joined Richards in 2008 and has been in the valve industry since 2002. Because we have quite a few of attendees this morning, we will be muting the phone lines. If you have any questions, there is a question chat tool built into GoToWebinar. If you would, please just type the question, and I'll get it answered as soon as we get to a break. With that, I'm going to turn it over to Tim.
Thanks, Mike, and thanks to all the attendees. I think you were promised in the invitation that this would be short, and we know your time's valuable, so we'll definitely keep our word on that. Just a quick run-through of agenda items. All right. Have to go the old-fashioned way. Just quickly, we want to go over a few different things, all of it pertaining to fractional or low-flow controls. On the agenda, fractional flow scope, kind of want to define the marketplace, and then we'll lead into some prevalent applications that we see. And that'll include a pretty diverse group of industries, and hopefully there'll be applications that are pertinent to each and every one of you. And then we'll go into some of the typical control valve design options that are out there in the market. And then we'll talk about some sizing and selection considerations that might help you out for these applications. And then we'll go a little bit beyond control valves and talk about some other products that may be applicable. And then lastly, we'll just offer some valve selection tips. And again, as Mike said, there's a dialog box. If you have questions, type them in, and then at the end of this, we'll have a little Q&A. Application scope, what we see as being the commonality or common denominator with all these is a small volume of some kind of product, liquid, gas, whatever it might be, that is being controlled, and the control requirements are for a high level of accuracy. And that's probably the most generic definition that I can give. And that may conjure up specific images, small products, pretty mundane applications. But within that scope, there's a lot of variety. For instance, if you look at temperatures, we see applications that run from cryogenic to temperatures over 1,000 degrees. And then within pressure, we see applications that are from vacuum to over 10,000 psi. And then the actual valves themselves, you can have your basic steels and stainless steels, things like that, but we see a lot of applications that require exotic alloys, whether it's due to chemical compatibilities or temperatures as listed above. So definitely some common things there with small amounts of flow, again, whether it's a gas, liquid, whatever it might be, but there's certainly a lot of different applications within that definition. First, I'm going to talk about some generic applications that we see, and we'll see this across a variety of industries. A lot of process and specialty gas applications, a lot of analyzer applications, a lot of sampling systems, R&D labs, that type of thing. And I want to segue that into some specifics. A couple of big markets that we see are pilot plants. A lot of the business that ourselves and other manufacturers see revolve around pilot plants. And these can range from just a small skid, as many of you have no doubt seen, all the way up to multi-room, depending on what they're trying to do. And what these typically have in common is you've got an existing process that a client wants to improve, or you have a new process idea and you want to validate that. And the idea here is to build a small-scale version, prove that technology or validate that improvement, and then scale it up to large scale. So you save a lot of money, obviously, by going with the pilot plant. And this is where your smaller valves, your lower flows come into play. Within the pilot plants, we see a lot of applications for acid injection, chemical dosing, and general metering. Another very prevalent industry is water treatment. This can be water treatment or wastewater treatment, and this can be standalone actual water treatment plants. But we also see a lot of these applications at refineries or chemical plants where they do their own water treatment, even if it's just to treat water before it goes to drain. A lot of the applications we see revolve around pH control. We see a lot of sulfuric acid applications, typically require alloy 20 material. We see a lot of caustics. We see sodium hypochlorites, usually you'll see Hastelloy C, and that's disinfectant, so that's going to be on water treatment side. But one thing of note that we see in these industries is a lot of the configurations have electric actuators as opposed to pneumatics, and that's just driven by the fact that a lot of these plants or treatment facilities are pretty big, and so they don't necessarily have air at their disposal to power pneumatic valves. Some of the other applications, and the idea here on this slide and the next one is to cover a lot of different technologies, a lot of different manufacturing and process applications, so that hopefully something will make sense to each of the attendees. We do a lot of corrosion prevention in petrochemical and oil and gas. We do subsea. Ammonia injection skids is a big application for pollution controls. Uranium enrichment, air separation. Again, cryogenic was mentioned earlier, and it can be gasification. There's applications for that where you're taking like liquid natural gas and expanding it out to actual gas, or freeze drying. We do a lot in the food industry with these type of applications. Helium gas, heavy water, chromatography skids is a big industry for these types of products. Hydrogen control and fuel cells. Carbon dioxide, again, pH control. Also atmospheric test equipment for the aircraft industry, and that's kind of an interesting one where they'll use these types of products to basically replicate flight, changing pressures and changing temperatures to test various aircraft equipment. Reactor pressure relief valves, humidification skids, and this can be in actual industrial where you need humidification going to a turbine, for example, or it can be as simple as climate controls in storage areas, maintenance shops, things like that. So very diverse applications there. Automotive test stand applications, typically tied to emission controls and engine component life testing. Bellows sealed versions is a very prevalent application where you've got some type of process that can't be leaked out. Hydrogen obviously is listed, and you don't want that getting out of the valve. So Bellows sealed applications. Steam pressure. Again, a lot of people, when they think of low flow or fractional flow applications, will kind of pigeonhole it as small amounts of process and not really tough applications, but there's a lot of applications for steam control with these types of products also. Hot oil skids, and then within the biofarm industry, there's also applications. I don't want to get into too much detail, obviously, but reactor sterilizers and things along those lines. Again, the idea with those two slides is hopefully there will be some application that's germane to each of you. There's a lot of different manufacturers of fractional flow products, and within the industry you'll see a lot of options. most of the applications are addressed with control valves, and I'm just going to run through some of the commercially available options that are out there. And the idea here is, maybe you've had some applications and you've used standard control valves for them. This is just to give you an idea of what's out there, what's commercially available. Maybe some of this will stick. Cryogenic bonnets. Again, we mentioned earlier gasification. We mentioned freeze drying, and all this does is isolate the packing up in here so that if you get an ice ball on the actual valve, it won't freeze the stem and bind it within the packing so that the valve will still modulate. And you see this down, typically, again, industry-wide, down into the 425 range is very prevalent. Bellows stem seal, which we touched on a little bit earlier. So you've got an actual bellows in here, and the idea is zero leakage. And as I mentioned, hydrogen earlier, but there's a lot of different chemicals, a lot of different gases that can't be released to the atmosphere, and this prevents that. Most manufacturers do have some type of leak detection port also. So then in the event of a bellows failure, you'll have a backup packing, and that leak detection port tells you that there's an issue. Again, I think just about anybody in the industry has that as an option. A less expensive alternative that's commercially available to the bellows is a double packing. Bellows can be expensive. Double packing puts a packing above and below the leak detection port. And again, same thing here. You've got two barriers essentially that your gas or your fluid would need to go through before you had any stem leakage or anything along those lines. High temperature. Couple of different ways that manufacturers will deal with this. Sometimes it's an extension, again, to get the packing away from it, and then some manufacturers also have a fin bonnet. It's just a simple heat sink that I'm sure all of you are familiar with. But again, the idea here is to think about these products as more than just kind of a generic niche kind of thing, because you can apply these onto applications that even go above 1,000 degrees F. Graphite packing obviously used at that point, and most of the manufacturers out there will recommend the use of a positioner at that point because graphite packing can bind on the stem a little bit more than a Teflon packing. Another commercially available product is thermoplastics. A lot of times, depending on chemical compatibility, this can be a lower cost alternative to an alloy, a Hastelloy C or an alloy 20 or something along those lines. So again, commercially available out there, a couple of different types of thermoplastics. Pressures are obviously a lot lower, but you can get these with all wetted parts out of like a PVC or a Kynar even. So again, a nice alternative depending on cost, your price points, and depending upon pressures. And also three-way, so if you had two different materials that you're blending, you can have a couple of inlets and a single outlet in order to make that happen. Again, fractional flow applications, so small amounts of flow through the valve. One of the important things with any of these type of applications is accuracy. Again, we're talking about metering or dosing small amounts of something into a larger product or a larger vessel or into a flow stream. And one way to enhance the accuracy of any of the control valves, and this is offered by any manufacturer of these type of products, would be a positioner. And all this does is it has some type of linkage or reference to the stem, and it compares the stem position to the input signal, and then it can add or take air out of the actuator to make any necessary corrections. So you get two things essentially out of the positioner. Typically you're going to get more accuracy, and secondly it can increase the differential pressure capability because it has the option of adding more air in order to push or locate the plug in the right spot based on the input signal. So again, accuracy is a big key here, and this is one step that most manufacturers offer to enhance that. And we briefly touched on electric actuators when we were talking about water treatment, but again, this is another way that you can make the valves more accurate. Doesn't require pneumatics, which is a nice bonus, but typically your electric actuators are more expensive than pneumatics, but they're also more accurate. So kind of comes down to your preference and your need for accuracy, and most people will have a good feel for that, and they'll know whether they can get by with a pneumatic, straight pneumatic, or whether they need pneumatic with a positioner, or whether they need to make the step up to an electric actuator. And electric actuators come in a lot of different thrusts and accuracy and things along those lines. So there's even options within electric actuators. And you might wonder, why is that important? Because that's going to help your rangeability. And these are representative rangeabilities. These are going to vary by actuators and by positioners. But this gives you an idea of the range of flows that you can accurately control through these valves. It's going to be CV dependent, and that's why there's some ranges up there. As you get into the lower CVs, the trim components become very, very small, so it becomes difficult to control over a larger range of flows. Again, these are all kind of representative of what's out there in the industry, and these are based on an electric actuator, the use of a positioner. If you don't have those ratios are going to be smaller. Some sizing considerations, and this is talking about picking the right orifice, the right plug, in order to make sure that you actually get the control that you're looking for. Low flow products, they have their own flow characteristics, and this typically occurs when you get into lower CVs. What we found is in liquids, when you get below 0.2, and in gases 0.05, they're no longer a laminar, or they're non-turbulent at that point. And I've got a little picture on the next slide to give you a graphic illustration of that. But what happens is when you get into the smaller sizes, the velocity at the center of the pipe or the valve is moving through there faster than what's on the outside. So it can be twice as fast, and this impacts the amount of flow that you're capable of moving through a valve. So at this point, the flow can be changing from turbulent to laminar. So now your CV is no longer a constant anymore. Now, typical sizing programs will assume a turbulent flow, and this will give you some bad calculations at times, depending on the fluids and the CVs that are involved. So the broad picture here is there are commercially available sizing programs. We have one, obviously, but you want to make sure that when you size these types of applications that you're using a low flow, a fractional flow type of sizing program, because they will compensate for any transitional or laminar flow. Here's a picture of turbulent flow. Typical flow through, if you had the molecules, you had your fluid going through, they're all going to move at the same speed through the pipe. When you get into the smaller pipe sizes, the center will go through faster. And again, that's what we're talking about. Now, it may not sound like a big deal, that, okay, a little bit of the fluid's moving faster. But again, we're talking about high accuracy applications. And knowing that the center can be moving twice as fast is critical. And again, you don't want to have the wrong CV, because you may not get the performance that you're looking for. You may not get the flow that you require. And you may not get the turn down that you need either. So it's very critical to make sure that you use the right sizing program. And just to reinforce that point, here's a representative chart of commercially available CVs. So again, starting at 4, you can see that you can get CVs down into the 0.00001. So again, that's why it's so important that you use the right program, because it'll help you select the right CVs. The difference between a 0.02 and a 0.01 may not be a whole lot in terms of flow, but one's double the other. So picking the right one is going to be very important. Additional products. And basically what we're going to talk about here briefly are some of the mechanical products that are available. What you're looking at there, a high pressure regulator, and all this does, mechanical device that knocks down an inlet pressure to an outlet pressure that you decide. Different spring ranges are available, and you can see on the slide pressures to 10,000 psi, maybe even higher, are commercially available, and you're just knocking down an inlet pressure to a lower outlet pressure. But it's nice to know you can do that in a mechanical product, and if that meets your accuracy needs, it's going to be a lot less costly than a control valve and a control loop and a pressure transmitter and all those type of things. Typical bar stock construction is available from just about anybody in the marketplace, and so that way you can get alloys and things like that also, depending on your compatibility needs. And there's also back pressure versions of it where it's a normally closed product and you're controlling the inlet pressure. So if it reaches a certain point, the valve opens and bleeds off the pressure. Again, whether it's a liquid, gas, whatever it might be. Again, you can get into the thousands of PSI. Bar stock is the most prevalent type of material used, so you can get alloys and things along those lines. Again, mechanical approach to some of the same applications. And then lastly, and I'm guessing just about everybody's seen these, just basic cylinder gas pressure reduction. Welding gases, helium, lab gases, R&D, pilot plants. Everybody seems to have the gas tanks sitting around at some place within the cage, and these are just great ways to reduce the pressure on those for user points. And just selection tips, and everything here is based upon accuracy and ease of changing CV. So one thing I'll point out, not everybody does this, but when you make selections, you ought to look at manufacturers that use a rolling diaphragm. Some of the manufacturers out there use a formed or pressed diaphragm, and as this valve strokes, as the stem goes up and down, the usable surface area, the effective area of the diaphragm on a formed diaphragm will change, and that becomes a variable. You want the thrust to be a constant. You want the only variable to be your input signal. So if you have a rolled diaphragm, as the valve strokes, the effective area remains constant. Therefore, again, your input signal is the only variable, and that's going to give you better control. A lot of the commercially available valves have a quick change trim option. Some manufacturers have it as a standard offering, in fact. And what this allows you to do is separate the stem below the actuator so that you can pull the plug and change the plug very easily. And to some of you, this may not be a big deal at all. You'll purchase a product and put it in, and it's going to be the same application over and over and over. But this is very prevalent in lab, R&D, and pilot plant applications where they're constantly changing flow requirements, applications, and things like that. And what this does is allow you to use the same valve for a lot of different applications simply by changing the trim. So therefore, you're saving a lot of money. And along with that, this is kind of the bottom half of the valve. You can see that a lot of the trim components will be held on by a bayonet connection. So you slide that plug, whoops, sorry about that. So you slide the plug down as mentioned previously, and the plug pops off there. And what's helpful in those applications is a bolted type of bonnet also. So if you have to change the CV, you have to change the flow characteristic, or you're just doing maintenance, a bolted bonnet will allow you to leave the body in line so you don't have to break down your actual process line. We've already talked about changing the plug, and then most manufacturers offer a removable seat. This particular one is threaded and actually comes out with your Craftsman deep well socket. So very easy to change the seat and plug to change again, CV, flow characteristic, or if you're just doing general maintenance. Questions? Oh, that's not what I wanted.
Tim, I don't have any questions at this point.
Okay.
I think what we could do is start to wrap up a little bit, and if a question comes in, we'll go ahead and get it answered. Tim, thank you very much for your presentation. If anybody does have a specific application question, feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you're not sure who to ask for, just go ahead and ask for me, Mike DeLaCluse. If you prefer to send me an email, my email is miked, M-I-K-E-D, @lesman.com. Next month, our webinar will be December 17th at 9 a.m. It'll be presented by Bob Stahl from Honeywell. The topic is going to be about safety integrity levels, or SIL. And basically, it's going to be a SIL 101 course. What do the standards mean, and how do instruments play a part in it? We will be sending out invitations shortly. So if you have any, if you're interested in that, please sign up. I do have a couple questions while we've been wrapping up here, Tim.
Okay.
First question
I can't see them. If you can read them, that'd be great.
Yeah, I'm going to read them so that everybody knows what they are. Do these valves require filtering for dirty service?
I don't know if that's a reference to the air to the actuator or the actual valve, so I'll answer both. Yeah,
I would consider it the fluid the valve is going to see.
Yeah, ideally, you're always going to have a filter before any control valve or any instrument, period. So yeah, especially as you get into the lower trims, the ports can be very small. So yeah, ideally you would have some kind of filter or a strainer or something like that upstream of these valves.
So the solutions that are really available for that sort of thing, really you want to put a strainer in, right?
Yes.
Okay. And we have access. Go ahead.
Yeah, we recommend, if you look at our basic I&M for these, in any CV or any line size, we always recommend a strainer upstream of the valve.
And what's the process of sizing the strainer? What do you have to do to make sure you put the right strainer in?
Generically, we recommend 40 micron strainer, and I think it states that in might state that in the I&M. Not 100% sure, but generally speaking, when we get that question, we recommend a 40 micron mesh strainer.
Okay.
Anything else?
Those are the questions. No, those are the questions we have at this point. Again, if anybody in the audience does have a further question, feel free to send it to me. You can either give me a call or send it to me via email. And again, my email is miked, M-I-K-E-D, @lesman.com. At this point, I don't have any further questions coming up, so we might as well conclude the presentation.
Okay. Well, thank you to all of you who spent the time with us and came in just under a half an hour as we promised. We know your time is valuable. So again, thank you for your time and your interest.
All right, Tim, thank you very much.
All right. Take care.
All right. Yep, bye.